So this is going to revolve around a lot of tools and techniques towards getting shellcode and using it quickly, as opposed to trying to manually build shellcode for the 1% off case for some weird platform you've never heard of. My agenda for this presentation is going to be a review of what stack smashing is, because right at the end of it we're going to need to know what we use shellcode for, and we're going to learn that it's memory corruption, but shellcode is where we introduce code to execute after diverting the control flow of a different program. What is shellcode? I have a slide on there and like the history, it's like 2 sentences. Don't worry about it, it's not a history lesson. And then some of the basics, and then we get into a little bit more specifics in terms of what I've seen shellcode-wise in CTFs before. And one of the big things that's always hit is alphanumeric shellcode. They'll run it through a function that pulls your shellcode and says, hey, we can't use this because it needs to look like it would be some sort of printable ASCII string. So, stack smashing, if you pronounce it. The high-level thing is we're overriding the instruction pointer. The instruction pointer dictates where we're going to go next in the program. And so in any vulnerable program like we have up here, these are slides that I took from the memory corruption presentation I did last semester. This is just something that will print your name. It reads it in, and if you overflow it, you get control of the instruction pointer, and you can point it right up there to that handy shell function. So if you throw in a couple A's, it works. Near the bottom there, we're using our favorite tool, Radair2, excuse me. Hello, AAA, and it works. Sweet. Well, happens if we throw 50 into it. It crashes. Getting segfault right there. But if we look at our registers, we see that over here in our instruction pointer, the IV, we have 41, 41, 41, 41. That is AAAA for people who love their ASCII. So we have hello AAAA and a crash. But the fact that we overwrote the instruction pointer is what is critical here. Didn't need that, could have gone here. Cool. So the instruction pointer guides where we're going next. And so it's trying to go to a memory location that's called 41, 41, 41, 41, which we cannot access. So what do? We can send our instruction pointer here to this very conveniently placed shell function. It takes in a parameter that is the command that it executes with system. And so this is the high level of what a stack is. When you're going into a function, it's going to read off of the stack what those first arguments are. So the first argument that's pushed onto the stack outside of the location of the function is going to be our argument. So we need to pass both the location of that function and either a pointer to our command string or the command string itself. And if we go over here, we can use our favorite tool again, Radair2, to find the location of that function for us. I'm going to go pretty fast just through this section, but I'm going to slow back down once we hit the shellcode stuff. We're hitting new material. So as you guys have memorized by now, I'm sure, your auto analysis stuff for Radair, and then AFL to get a list of the functions. If we look up here to sim shell, that is a location that we need to put, or that we need to overwrite our instruction pointer with. And also, very fortunately, we have a string already baked into the program that's /bin/sh. So we can just throw that right onto the stack too. So this is our amazing command. We have to throw in an extra junk value in there because this one is expecting a return pointer right after the argument, but it's the exact same principle. We have 27 bytes before we write over the instruction pointer. We have the location of the function pointer for, what's it called? For shell, and then we have a pointer to the string for bin sh. Awesome, we win. We did it. We smashed it. Awesome. So what is shellcode? Well, it's a set of instructions that are going to execute in the program that aren't typically there. Usually when you're building exploits or you're doing any sort of exploit development, you need shellcode 99.9% of the time because no one just bakes in a let me win function. No one says, all right, let me add exec bin sh. Or at least you should. Stop it. So you use shellcode to add in that functionality, and then you need to jump to your shellcode. Where did it come from? These are the 2 sentences I promised you guys. Well, that's what it is in C. It is 5 lines, and it literally just gives you a shell. That is the entirety of where the name came from, so you guys can feel super smart, like I do now, that I know where the term shellcode came from. So shellcode is x86. It's going to be a bunch of instructions that ultimately call a syscall to do something that you want to do. You're not limited to that. You can do just about anything in the programming language, given that it's position independent as well. So we can also see it as a string. Yeah, that is how you could pass /bin or exec bin sh. All right, hello world shellcode. Exact same principle. You can code just about anything in shellcode. If you're familiar with assembly, notice we have a label here, and then all we're doing is we're using a Linux syscall to write out to standard out, and we're pushing the bytes, so these guys, as the ASCII values for hello world. And then we're exiting over here. Nothing terribly crazy, but nothing we really want to dive into if we're not trying to study assembly. Awesome. Now we know what stack smashing is, we know what shellcode is. Let's get into some of the basics of what it is. Compiling shellcode. If you're crazy enough to try and write some of your own shellcode, you're not going online, you're not Googling it, you're not looking for any shellcode builders, there are a number of tools that you have at your disposal, usually just on any general Linux system. NASM will let you compile shellcode into an object file, which you can then open up and look at if you're still crazy. And then this is the process that you would go through to do it. Again, our shellcode is a string right there for bin sh. This is just something I wanted to have in the slide in case people wanted a review of the stages of compilation. This is something you would go over in CS 262. I'm not going to stress it in terms of the CTF context because generally they let you know when you need shellcode, or it's obvious when they don't have a win function. So what does it look like to test shellcode? So if you've just pulled shellcode from online or you're building it, you're going to need to test it. You want to make sure it works, you want to make sure it crashes, you want to make sure it lets you read the flag from the server. And so you need to do a couple things to do that. And one of the most traditional ways to do that is to build a C program that doesn't really have a name, but that lets you arbitrarily execute shellcode. And down here is the magic of it, where it jumps your instruction pointer to the very beginning of the shellcode and treats it like it's executable, like it's mapped memory that is executable. So it can just arbitrarily start running shellcode. So this is the hello world example from earlier, treated entirely as though it were shellcode. And we can see, I compiled it, I made sure there was an executable stack, and I ran it. And I got hello world. Awesome, it works. All right, so now that we're not in the 1990s, there are some much better tools that you can use to build shellcode. And namely, they are Pwn tools, and there's also shellcode test. And then at the very end, I'm going to talk about a tool out of the Metasploit framework, which makes a lot of these tools even seem obsolete too. But so the main 2 things that you want to know between them are the ASM and disasm commands. So ASM will let you assemble it if you pulled shellcode offline, or from online, and you're looking to understand how it works. You can disassemble it and get the individual instructions, or you can reassemble a given set of instructions and build your shellcode dynamically. They have way more functionality than what I put on up here. Looking at the help menus for the Pwn tools thing is absolutely critical. You can pipe assembly and disassembly into these and read it very quickly. You can disassemble things and you can have it print out very nicely. You can have it switch syntax. You can have it do all sorts of cool things. I think I said cool 3 times. All right, now we're going to slow down a little bit. So why do we care about shellcode? Why doesn't everyone just use the exact same bin sh that you can Google and get offline from Package Storm every time? Well, in CTF problems, they love to throw constraints at you. They'll say you can't use the letter A, you can't use the byte 37, and it has to be less than 40 characters. So up here we have a couple examples of what that sometimes looks like. And these are very common string functions that are used to read in or parse a given input to a program. And so these are some of the most common ones where we have null bytes. If you've studied C strings in any programming class, you know that a null byte indicates the end of a string. So obviously, if we're feeding in a string to this program and we're asking it to execute on it, it's going to stop right there, and it's not going to see the rest of our shellcode. Similarly, we have new lines. If it's only reading to the end of the line and it sees that byte, it's going to stop reading it again. So even if it looks like a valid instruction that's 6 bytes long, if it has any of those bad bytes, as the terminology is known as, it won't read it in and it won't execute it because it just can't be placed into the stack or the heap to be executed. Similarly, there's one additional thing that usually throws people when they're starting out. It's Indianness. When you're putting stuff onto the stack, our computers generally interpret it as little Indian, which is just fancy speak for saying it gets put on backwards, because that's easier for the computer to understand. So if I'm trying to put in ABCD on the stack, it actually looks like DCVA. And so you have tricks in Python, like the pack command, or you can go into Pwn Tools and have it flip it for you to get around this. But this is frequently a frustration for people first getting into shellcode, as they'll have perfectly valid shellcode that's null-free, they have it all set up, it points to the right location, but they literally have it backwards. I have a nice diagram right here that I absolutely stole from RPI-SEC's page on shellcode. It's the exact same thing. That's your stack building up, and then that building up, and that's how we're placing our shellcode on there. Sorry, our address at that point. Awesome. So alphanumeric shellcode. So this is one of the most frequent things that I see in pwnable shellcode constraints. This one's right. And all it's saying is that it can only accept ASCII characters. And this can be an issue if you have an instruction that doesn't have any equivalent in an ASCII character. So there are a couple ways to get around it. One of which that I'm going to recommend here just for ease of use is an encoder. And what it'll do is it'll translate an instruction into semantically the equivalent of 4 or 5 instructions, but where you might have add 1, it might be add 2, subtract 1. And they're going to look very different on the stack, and they're not going to have those non-printable characters. Oh, sweet, I have it on here. Functions like is alphanumeric might be used in CTF problems to see if you're passing in any non-alphanumeric shellcode, and then they would stop you right there. So this is an example of what it might look like for alphanumeric shellcode instead of, this is what it might look like to swap out an instruction for alphanumeric shellcode. So EAX is a register that you would frequently need for a syscall. So if you're trying to read the flag, if you're trying to run exec for binsh, this is something where you could, for example, increment a register or decrement a register instead of straight up adding 4 or subtracting 4, because we can represent each of those instructions as ASCII values. Yeah, just like I said right there. You can generally do what you need to do. There are some instructions that there is just no semantic equivalent, and you just have to work around that. But usually there's a published workaround about how to get around it, and usually your shellcode just expands in size. Shellcode generators, awesome. So very first thing, there's definitely a crap ton of shellcode that is online. Packetstorm, ExploitDB, Googling around and finding someone's blog post. Just about everyone in the world, that's figuratively speaking, has made a binsh shellcode. But if you're looking for anything more specific, like a catflag.txt, it might not be up there. So that's when we're going to have to switch to shellcode generators. That red did not pop as much as I'd hoped. Darn. So Metasploit has an awesome shellcode generator. They usually recommend it for penetration testing, but there's no reason why you can't use it for CTFs. It's called Metasploit Framework Venom, and it lets you build a null-free, alphanumeric, encoded. You can constrain the size, and you can add a whole bunch of things to it, like knobs, and that's awesome. So here's an example of how complicated this tool can be. So over here, I had to spell out MSF Venom. I can tab quickly with that one. And I said I wanted 64-bit Linux and execute this. After sweating for a while, I was given my payload. And this is literally outputting the raw bytes. So if you were a bash guru, you could even work that into an offset you might have. If you needed to overflow 300 bytes before trying to redirect your instruction pointer to that point of your buffer. And you have less typical things like reading a file. So if I wanted to call a read file because there's a sandbox around running binsh, there's shellcode out there that lets you open up a file and read it. It will literally call the Linux syscall read on whatever file you give it, and it'll spit it out right to the screen. Oh man, and I should have escaped that tilde, because you can translate that tilde into their side. So where it says /home/chris/flag, that could actually be /flag. And that's a trick that I've liked to use before, because usually when you exploit a box, they just have it in their home directory, and it's flag or flag.txt or .flag if they're trying to mess with you. So that's a really cool trick to use when they're trying to make you do something much more complicated down the exec route. And then finally, if you guys are not willing to go and Google every single instruction and swap it out for alphanumeric shellcode, there is also an encoder for Metasploit Venom to swap all of that out for printable characters. Contrary to popular belief, these question marks down here are actually printable ASCII characters. I know that was the first thing you guys were thinking about, but you can actually print those out, and they're within the ranges. Then, if you want to do a full exploit, so we have our command up there, we have an alphanumeric piece there, we have a knob slit up here, and we want to put this into a Python format for our exploit because we're running it through Python. It can do that. And right here we see it's assigning a variable buff and throwing all of our shellcode into there in a little Indian format. So they take all of the hard work out of building the shellcode for us, which is really nice of them. And if you guys are interested, using these tools, you can actually solve 4 problems I have hosted that Michael Bailey has been so kind as to host for us. I have both the binaries and the source available at this Google Drive link. Which
if you go to, it should work. It's IP whitelisted, but if you go to just caffix.competitivecyber.club, it'll redirect to the Google Drive link. It should. If it doesn't, somebody tell me, and I'll just release the blacklist on the IPs.
I know I went pretty fast, but I wanted to try and get some of the problems out there so I can walk around and talk with some people about what techniques you might be trying to use to solve these.
Also, if you're wondering where the ports are, they're also commented in the source when you look at them in the Google Drive. Like, it'll say up there, like, instructions to run, SOCAT, blah, 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 port 7701. It'll be on caffix.competitivecyber.club, port 7701.
Take it there are no questions. Thank you guys very much.